Quickly before we get started, I just wanted to give you an overview and the rationale for why I developed Chem Companion. And essentially, it's the fastest way to learn chemistry. And in medical school, we have a ton of content to learn and not a lot of time. So we need to figure out what is the most high yield? How do I get the biggest bang for my buck? So what topics are going to get me the most information, the best information, the fastest so I can do well on my exam? And essentially that's through practice problem walkthroughs. So we see the question, we walk through it, we see how it's solved, and that's how we learn the most the fastest. So what I've done is I've developed multiple practice exams that are essentially 20 to 30 questions long that are walkthroughs of these practice exam problems that you'll see on your actual chemistry exams. So Chem Convention was developed at the behest of my tutoring pupils. So I've been tutoring chemistry for about 10 years now, and my students are like, wow, is it really that easy? I wish my teacher would have taught it like that. So since they told me that, I was like, well, how do I get this to more students? So I built this online course so I can reach more students, and I've developed a course here that's currently under construction, but it's going to be at teachable.com under Chem Companion. And so please leave a comment on this video to let me know how I can improve this content, and please enjoy this exam one walkthrough for free. Welcome to Chem Companion. The following exam problems are from exam 1A, and so this corresponds, if you're a Texas Tech student, to Chem 1307, fall 2019, midterm exam 1A. And so remember, these are completely unique problems that I have designed that are similar to the problems in these various practice exams that other schools give out. So remember, these are unique problems I've designed that will help you learn the concepts, and then you can go back and use those practice exams as sort of a simulated exam.
What is the coefficient of C3H8 when it is combusted? Okay, so what we're looking at here is the coefficient. So that's the number that goes in front of the products and the reactants. And so one thing that we need to know here is combusted. So what are the two products that you always get from a combustion reaction? Okay, CO2 and water, right? And so one thing that's kind of assumed that I've already written in here for you is that oxygen, and remember, elemental oxygen, O2, is written as a diatomic, right? It's one of the diatomics. Okay, so some chemical is going to be combusted with oxygen. So when you hear combustion, know that one of the reactants is oxygen and the two products are CO2 and H2O. Okay, so we need to find the coefficient in front, and so essentially we need to balance. So let's start off, see we have 3 carbons here. I start with carbons first, or any non-oxygen, non-hydrogen. So C3, so let's just start by putting a 3 here and see where that gets us. So now we have 6, 7 oxygens and 2 hydrogens over here. So we have 8 hydrogens here. So let's go ahead and put a 4 here and see what we have now. So now we have 3 carbons and 6 oxygens here, 4 oxygens here, 8 hydrogens. So I like to do, we just write out CHO, and then we can get a total going for each side. Right, so we have 3 and 3, so we're good there. We have 8 and 8, so we're good there. And then over here on the left side, we have 1 and then 3. So that's not going to be particularly good. Let's see on the right side, how many do we have? We have 6 plus 4, so we have 10 over here. Because basically any number that we put in front of here will, when added to the 1, will give us an odd number. So there's like no way that we can get it to add up to 10, right? So what we can do is, this is a trick I use, if normally when you're in this situation, just double all the numbers, right? So by doubling this, then this would be a 6, right? And then this would be an 8. So now let's see where we're at. So we've got 6 carbons on each side. How many hydrogens is that now? 16. And then on the left side, we have 2, 4 oxygens over here. And now on the right side, we have 6 times 2, so that's 12. and then 8. So we've got 20 now on this side, right? So all those numbers just doubled. So we've got 20, and now we have the left side, our first term here, that gives us those 2 oxygens plus, and then what goes in front of the oxygen here. So that's going to be a 9, right? So because 9 times 2 plus 2, that'll give us the 20 that we need, right? So then we have 20. So what is the coefficient? C3H08 in isopropyl alcohol? That's going to be 2. How many grams of water are present in 75 moles of water, right? So we're starting, always write what you're starting with. You have 75 moles of water, and we want to go to grams, right? So I always put the first term over 1, multiply by, okay, and so what is the molar mass for H2O? So H is 1.01, oxygen 16, and we have 2 of these, right? So that's 2.02, and then 16, so you have 18.02 for the molar mass, right? So if moles of water is on top, moles has to go on the bottom. So for every 1 mole of H2O, there are 18.02 grams. That's how much 1 mole of water weighs, 18.02 grams. So we'll cancel out. The units that are left is going to be grams of water. And 75 times 18.02 gives us 1,351.5 grams, which is equivalent to 1.352 kilograms if you do kilos of water. Just a side note here, know that 1 milliliter of water is equal to 1 centimeter cubed, cubic centimeter, or cc, right? So we have 1 mil of water is the same thing as 1 centimeter cubed of water, which is the same thing as 1 gram. So 1 gram of water is 1 centimeter cubed is 1 milliliter. Okay, so here we have a unit conversion problem. Unit conversion problems are extremely important because if you know how to do unit conversions, the rest of chemistry is pretty easy. So how many centimeters cubed are in 167 millimeters cubed? So let's say 167 millimeters cubed. I always start by putting it over 1. Okay, so the units here, millimeters cubed, that's the same thing as saying like millimeters times millimeters times millimeters, right? So it's cubed, all 3 of those. So whenever we're multiplying, we'll have to do millimeters, millimeters, and then another millimeters. So essentially we have to do it 3 times. And how many millimeters, what's the next unit up, would be centimeters, right? So how many millimeters are in a centimeter? 10. Right? So when we multiply this out, millimeters cubed will take care of those units. And then centimeters will be centimeters cubed because we have centimeters times centimeters times centimeters. And then we have 167 divided by 10 times 10 times 10, right? So what we're going to end up with is 1, 2, 3 zeros, 1, 2, 3. So 0.167 centimeters cubed. Okay, so definitely go review your sig figs. So a lot of times when it comes to sig figs, this question will specifically ask you. So some professors, they require you to do every problem in sig figs. Sometimes they just, or it's only on specific problems like this one here. So we have 10, 8.58. So let's look at the significant figures here. So here we have how many significant figures? 1, and then this one's trapped, right? So 2, 3, 4, 5, right? Because it's following the decimal. So here we have 5. Over here we have 1, 2, 3, because they're all non-zero. 2, and then here we have a trapped 0 here. So that's still 1, 2, 3. And essentially, when it comes to sig figs, you are only going to be as least precise as possible. So talking about precise meaning like how many decimal points, right? So this one we've got 3 decimal points. This one we have no decimal points. So you can only be as accurate as your least accurate number, which would be the least number of sig figs. So we're going to be looking at some number that has 2 sig figs. So essentially you can eliminate anything that has more than 2 sig figs, right? So you can just knock some of those out, which that was the one I meant to mark out there. So here we go. So the top is going to come out to 18.58. The bottom we have 128.32. And then this comes out to 0.14479. And then wait to the end to chop down on your sig figs, right? So here we've got 1, 2. That's a 4, so no rounding. So then our answer is going to be E. Which element has the most similar chemical properties to cesium? Okay, so down here we have cesium. What is it called when it's up and down? It's a group, right? So we have groups, and then what is it called when you go across? Those are called periods, right? So we have groups going down, periods going across, and elements in the same group, so going up and down, have similar properties, right? So one thing that really demonstrates this, if we come over here, silver and gold have very similar properties, right? And so you can think silver and gold are very similar. So that's one way you can remember that groups, or up and down, have similar properties. So which element has most similar chemical properties to cesium is probably going to be something in the group. So is hydrogen in the group? Yes, but it's far away and it's a little bit different from all the others since it's a gas and the rest are metals. Next is calcium, so we're right here. So we're getting warmer. Barium right next door. Then rubidium right here, and then lithium up here. So most likely it's going to be rubidium. It's in the same group. Barium's not in the same group, so most likely it's going to be rubidium. So D is the best answer. Sig figs. I get tired of those. So how many sig figs in this first number? 1, 2, 3, right? Leading zeros, which would be this one and this one, they're not significant. So we're dealing with 3 sig figs. And they want it in scientific notation. So normally you have the first number, decimal, and then your other numbers. Any integers in the expression of the scientific notation, any of the integers in the front are significant. So if we have 3.60 times 10 to the negative second, right? So we have 1, 2, 3 significant figures, right? So we have 3.6 times 10 to the negative second, and we're in meters, right? So that's going to be B. So here we have a temperature conversion problem, right? So we're converting 2.4 Kelvin. We're going to convert that to Celsius as well as Fahrenheit. So Kelvin is Celsius plus 273. You can leave it at 273. Some professors like to do 273.15. Anyway, so if we're going to calculate Celsius, we'll need this equation here. So if we have 2.4 Kelvin equals Celsius plus 273.15, that's going to come out to negative 270.6 degrees Celsius. Extremely cold. Okay, so also we need to do Fahrenheit. So the way you get from Celsius to Fahrenheit is Celsius times 9/5 plus 32 is going to get you into Fahrenheit. So all we need to do is plug in this number here, negative 270.6 times 9/5 plus 32, and that's going to come out to negative 455.08 degrees Fahrenheit. Very cold. It's important to know the relationship between units in the metric system. So here we're looking at grams. You can go up, so 1,000 is normally the units that you jump between. So 1,000 grams, that is a kilogram, right? So if we're going the other direction, what is 1/1000th of a gram? That is a milligram. 1/1000th of a milligram is a microgram. Then 1/1000th of that is a nanogram. So there's 1,000 between all of these units. So it's wanting the relationship between nanograms and milligrams. So it's 1,000,000th of a milligram. So that's how many zeros? 1, 2, 3, 4, 5, 6. So there's 1 million nanograms in 1 milligram, or 1 milligram, one millionth of a milligram is the same thing as 1 nanogram. So knowing that, let's look at our answer choices. So we said that 1 milligram is the same thing as 1 million nanograms. It looks like our answer is E. So be sure you can convert between these units. It's extremely important. And know that this relationship between gram, milligram, microgram, and nanogram, they're all 1/1000th or in 1,000 units between each other. Okay, so the elements in group 2A are known by what name? Okay, so once again, groups, we're dealing with going down, right? So elements that have similar properties. So that first group, second group, it's kind of like threes over here, 4, 5, 6, 7, 8. Okay, and it wants 2A, so 2A is going to be this group here. Okay, and let's look at our answer choices, halogens. So just so you know, halogens are right here. So that's group 7, not that one. Alkali, so alkali metals are group 1. So it's not that one. So alkaline, and the way I keep these straight is alkali alphabetically comes before alkaline. So alkali is first, alkaline is second. So these are the alkaline earth. Noble gases right here. Metalloids technically aren't a group. And then transition metals, right? So transition metals are in here, the D block, and then the metalloids are right up in here. So S is the element symbol for what element? Okay, so the one here at the bottom, so this guy right here, seaborgium is the only element that was named after a person while they were still living. And so seaborgium, this is him pointing at the element on the periodic table. There's a very famous picture. But seaborgium is S, you would think it's SB, but SB is antimony, which, yeah, I have no idea on that one. But seaborgium is SG. So that's just a little side note, fun fact there. He's the only person alive that was alive while the element was named after him. Selenium, I believe, is Se, silicon Si, scandium Sc, sulfur S, and then a lot of people will just go, oh, S, sodium. Sodium is Na, so don't get tripped up over sodium being Na. Normally, students use it enough for, sodium chloride is used for so many things that it's not that big of a deal, but it's going to be B, sulfur. Another extremely important concept is nomenclature and writing formulas in chemistry. I want you to be extremely well versed in this because on subsequent exams, you will be given the formula or the name, and it's assumed that you know that. And so a lot of students will not do super well on the first exam, not learn nomenclature very much, get into later exams, and then miss the question because of nomenclature. So I cannot stress how important this is. So iron 3 chloride, what is the formula? So iron 3, so we're using the Roman numerals, so we're specifying the charge on iron because iron can have multiple oxidation states. So iron normally exists as a +2 and a +3, right? And so we have to specify the charge because, well, if you just did iron chloride, iron chloride, iron chloride, right? So here, chloride is a -1 charge. So here, iron would be a +1. 2 chlorines, right? So that'd be -2. 3 chlorines, -3. So we have a +3, a +2. So you need to specify when it comes to specifically transition metals, what is the oxidation state? So when you're naming, you have to specify what the charge is because you can see here there's confusion. So we have iron 3, so we know it's this iron with a +3. And then chlorine, Cl, which has a charge of -1. So if you just use the rule where you bring it down, then you have FeCl3. That's iron 3 chloride. How many atoms of lithium are in 250 grams of lithium carbonate? Okay, so lithium carbonate is used in psychiatric medicine for the treatment of bipolar depression. It's kind of an older drug, so it's probably not as prescribed today. But lithium carbonate, so Li, that's lithium, carbonate. The carbonate polyatomic ion is CO3 minus 2. So know your polyatomics, right? So we have lithium, which is a +1. It's in the first group. So lithium carbonate, when we write this formula, right, so bring the signs down, it's going to be Li2CO3. That's lithium carbonate. And we need to determine the molar mass of lithium carbonate. So lithium carbonate, so LiCO. One oxygen is 16, carbon is 12.01, right? So we have 3 of these, 48, 12.01, and then lithium is 6.94 times, what do we have, 2 of those, right? So that's going to give us 13.88. Then when we add all of that up, we get 73.89 grams per mole. So we're starting out with 250 grams of lithium carbonate. So if we have grams on top, grams is going to go on the bottom. So that's 73.89 grams in 1 mole of lithium carbonate. Next, we can say, okay, well, 1 mole is how many atoms, right? So it's 6.02 times 10 to the 23rd atoms, because that's what we're looking for, right? How many atoms are there in 250 grams of lithium carbonate? So we know how many lithium atoms. So we have 1 mole is 6.02 times 10 to the 23rd. So if we multiply that all out, we're going to come up short, right? So for lithium carbonate, for every 1 mole of lithium carbonate, we're going to get 2 moles, right? Because there's 2 lithiums for every 1 mole of lithium carbonate. So we need to do 2, multiply that number by 2. And then that will give us our final answer of 4.07 times 10 to the negative 24th atoms of lithium. Blank is a diatomic molecule in its elemental form. Okay, so I really like putting this early on in the content because diatomics are used and they're assumed. So here we're going to look at which elements are diatomics. Di meaning 2, right? So together, 2 atoms. The diatomics, there's 7 that make a 7. Okay, so let's look over here. So nitrogen is a diatomic, so N2. Oxygen is a diatomic, O2. Fluorine, chlorine, bromine, and iodine. But that's 1, 2, 3, 4, 5, 6, right? So there's 7 that make a 7. Lastly is hydrogen. Okay, so all these elements, when they're in their elemental form, meaning they're by themselves, then it's represented as a diatomic, right? So if you're saying this element, right, so let's say, just throw something out there, we'll say lithium reacts with hydrogen. So you got to write it as a diatomic. Or if there's a combustion of some hydrocarbon, like methane, is combusted in the presence of oxygen, right? So we have to write the O2. So it is extremely important that you understand this concept. So be sure you know the diatomics, the 7 that make a 7, so the 6 over here on the right, and then hydrogen. So a nomenclature problem, gallium nitrate has the formula, so we need to figure out what the formula is. So gallium, notice we have the rooster here in France, so Gall, so it's named after France, essentially, gallium. So gallium on the periodic table is Ga, so anything that's not Ga on here, okay, so A, B, they're all Ga. So gallium nitrate. So nitrate is what? Well, it's either N or some sort of NO3, right? So it's actually NO3. What is the charge on nitrate? Okay, so that is a -1. And what is the charge on gallium? So gallium on the periodic table has a charge of +3. So it's in that column of the +3s. And then we're just going to bring these down. So we have gallium nitrate. So D. Here we have just a basic definition problem, right? So which of the following descriptions of a subatomic particle is correct? So a neutron has a positive charge. Okay, so we know that's already wrong because neutrons are neutral, right? So not that one. An electron has a negative charge. So far, so good. And a mass of approximately 1 atomic mass unit. Okay, so electrons are actually really, really small to the point where they're essentially negligible in some calculations. 1 AMU is essentially a proton or a neutron. So we're going to knock that one off. So a positron, so notice it says positron, has a positive charge and a mass of approximately 1 AMU. So positron is when we're dealing with radioactive decay, so that's not what we're looking for here. A neutron has no charge and its mass is negligible. No, because it's around 1 AMU approximately. Proton has a positive charge, so far so good, and a mass of approximately 1 AMU, so the best answer choice here is number 5. Statue of Liberty is made of copper, and it has changed from kind of the original copper color to this sort of green color. And we want to know what exactly happened here. So was it a physical change, chemical change, deposition, sublimation? And deposition is just when something goes from a gas directly to a solid, and a sublimation is when it goes from a solid directly to a gas like CO2 or like dry ice, right? So dry ice goes straight from a solid to a gas. Eliminate those two. So we're dealing with a physical change or a chemical change. Physical change is essentially the element identity does not change. So that's like if we have liquid water that's frozen into a solid, it's still water. It just had a physical change. Or the liquid going into a gas, right? So it's still water, it's just water vapor. So that is a physical change, no change in the chemical identity. Normally, when there's a chemical reaction, light is produced, a gas is produced, there's a color change, and there's a few others. But here we're dealing with specifically a color change, right? Change to green. So we're actually dealing with a chemical change. It's actually an oxidation process. Kim Kardashian's ring is 14 carats, so massive. What is the density of the diamond if its volume is 0.8 mils? Okay, so what are we asking for? What is the density? Okay, so density is, remember you love density. So kind of looks like a heart. So density is mass over volume. Okay, mass being grams, volume being milliliters, which is the same thing as saying centimeters cubed. So density is normally expressed as grams per centimeter cubed. So what do we have? 14 carats. That's going to be our mass, but we need to use the unit conversion and try to get it to grams. So if we have 14 carats for 1, and then using this horrible unit, I just wanted you to practice unit conversions. They're 200,000 micrograms in 1 carat. How many micrograms? What's the next unit up? It's going to be milligrams, right? So 1,000 micrograms in 1 milligram. Then what's the next unit up? There's 1,000 milligrams in 1 gram. So we finally reached the unit we want. All these units seem to cancel. So if we multiply this out, we'll get grams, and we're getting 2.8 grams. That's pretty solid. I just $1.5 million, 2.8 grams. Pretty interesting there. Okay, so we have density is mass over volume. So we have our mass, 2.8 grams. We have our volume of 0.8 milliliters or centimeters cubed, and that will give us our density. And the density comes out to 3.5 grams per centimeter cubed. One way that density is actually determined as well is you can submerge something in water, right? So let's just say we just have our diamond. We can put it on the scale and weigh it. Comes out to 2.8 grams. Then we can put it in water, right? And then we can see how much the water level changes when we add the diamond, right? So if it went up 0.8 mils, like if you were able to measure that sensitively, if it went up 0.8 mils, right, then we would be able to calculate the density. So this is an old school way of using water displacement to help calculate density. So the empirical formula of a compound, so some hydrocarbon, right, CH2, and its molar mass is 0.252 kilograms. What is the molecular formula? Okay, so how are we going to figure this out? First, let's take that and convert it into something useful. How many grams in a kilogram? Kilo, 1,000, right? So 1,000 grams. This unit is on top, so it's going to be on the bottom. So 1 kilogram, 1, 2, 3. So we have 252 grams. That's the molar mass, so that's grams per mole. Okay, so that's how much the whole compound weighs, 252. Okay, so the empirical formula, remember, is just the reduced form. So, right, so if we had like C6H12, the empirical formula would be CH2, right? So we're just reducing, divide by 6, then you get CH2. But this is asking for the molecular formula. So we want to calculate this type of formula. So we're kind of working backwards in this case. So we have the reduced form. So let's see. C is 12.01. H is 1.01. We have 2 in this case, right? So you're going to get 2.02. So when we add these up, we're going to get 14.03 grams per mole. So think of it this way. CH2 and C6H12. How many CH2s go into that? CH2, 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 right? So we need 6 of these. 1, 2, 3, 4, 5, 6. Okay, so what we've done here is we've actually figured out the mass of one of those parts. But we need to figure out how many parts are in the total. So if we do 252, that's the total, divided by 14.03, that will tell us basically how many parts we need to make the molecular formula. So when we divide that, we're going to get 17.96, which is about 18, right? So we'll just round that off to 18. So CH2, that's times 18. We need 18 of those to get up to the full molecular mass, right? So we'll have C18H36. So that is going to be the molecular formula. So I really like to think of it as, what does the one piece weigh? All the parts together weigh something. Divide by how much does one part weigh. Gives you how many parts there are. Then multiply the empirical formula by that many parts. Okay, so here we have a little bit of nomenclature practice. So dinitrogen monoxide, so dinitrogen monoxide, so di 2, mono 1, nitrogen, oxygen. Okay, so remember we use the dis, the monos, tris, and so on. We use that nomenclature when we're dealing with a nonmetal plus a nonmetal, right? So nitrogen and oxygen. So down here we have a metal and then polyatomic or a nonmetal. So we use a different type of nomenclature. Specifically with a transition metal, we'll use the Roman numerals. So up here at the top, dinitrogen monoxide. So we're just going to run through. Mono is 1, di, tri, tetra, penta, hexa. So what's after that? Hepta, oct, non. So that's 9 for non. So you can look these up, but the more you use it, you'll get used to it. Okay, so dinitrogen monoxide. So 2 nitrogens, monoxide, 1. Okay, and then with the molar mass of that. So nitrogen has a molar mass of 14.01. Oxygen has a molar mass of 16. 2 nitrogens, so that's 28.02 plus 16. So that's going to give us 44.02 grams per mole. Okay, next, iron 3 sulfate. Okay, so let's write this formula out. Iron 3 is a charge on iron. Sulfate, it's a polyatomic, right? SO4 with a -2 charge. Need to bring down Fe2, SO4, and then 3 of those. Okay, and the 3's distribute, right? So the 3 is going to go with the oxygen, with there's 4, so then there'll be 12, right? So let's look at this. So we have iron. So iron equals 55.85. 2 of those. Sulfur, 32.07. 3 of those. Oxygen, we've got 16 times 12 oxygens, right? So when we get all of that, it's going to be 111.7, 96.21, and then 192, which will give us a total mass of 399.91 grams per mole. So it's important to be able to name and write the formula, and this is just demonstrating that. Okay, so how many moles of sugar are in 1 can of Coca-Cola? So I'm assuming this is one 16-ounce or standard size can. So we can see down here at the bottom, 39 grams. So we're going to assume the sugar that they're using is just right here, just like some glucose. So 39 grams is what we're going to start with. 39 grams of C6H12O6. Okay. Moles. How do we get to moles? Right, well, we need to do grams to moles, so we need the molar mass of this, essentially, right? So C, carbon, 12.01, 6 of those. Hydrogen, 1.01, 12 of those. Oxygen, 16 times 6. And then we're going to come out with 180.18 grams per mole for the molar mass of our glucose or sugar, right? So let's do 39 grams of C6H12O6 over 1 times 180.18 grams in 1 mole. And that's going to give us how many moles of sugar there are in 1 can of Coke. And that comes out to 0.216 moles of C6H12O6. So what is the chemical name for HCl? Okay, so this is what trips students up when we're dealing with naming specifically acids. So acids essentially donate H, so if we dissociated HCl in solution, acids are something that donate H plus protons. So sulfuric acid, notice the H's there, right? Phosphoric, hydrochloric, right? So HCl, hydroiodic, hydrobromic, right? So you can see with these here, we're saying hydrochloric, hydroiodic, hydrobromic, okay? So that's how we name the acids, the binary acids that have a halogen with them, right? So that one's going to be hydrochloric acid. When we name some of the other acids, you need to remember 8 goes to ic, ite goes to us. What does that mean? SO4, that's sulfate, has a -2 charge. So if we write that out as the H2SO4 sulfuric acid, so the 8, the ion, sulfate, is sulfuric acid. SO3 minus 2, sulfite. So if we had H2SO3, that's going to be sulfurous acid. So you need to know 8-ic, us, and it's very useful. Another thing that's very helpful is whenever you're memorizing your polyatomics, remember all the ones that end in 8-te. So 8, so like sulfate, chlorate, nitrate. Then when you remove an oxygen, then it goes to ite. So like if you have SO3, sulfite, chlorite, nitrite. So just another useful tool. Write the symbol for iodine that has a mass of 131. Okay, so remember for writing kind of this standard, nomenclature or symbol, right? So AZ, so your mass is going to go on top, and then your atomic number is going to go on the bottom. So if we have iodine 131, it's going to be up here, and then your atomic number will be down here. So that is how you write iodine 131. So over here, the hat is just so we can make it a novelty or a parody so there's no infringement of certain textbooks. But this lady has what's called goiter. So this is what happens when you don't get enough iodine in your diet. Essentially, your thyroid uses iodine to make certain hormones, and essentially it's not able to make enough hormone, so it enlarges, so it can try to produce more, but it's not getting the iodine, so it can't do it. So it enlarges to compensate, so you get goiter. So that's why table salt, you'll see iodinized salt at the store. That's because they add iodine to reduce the possibility of goiter. That's why you don't see this in the developed world. Over here on the right, we can see a cold nodule versus a hot nodule in a thyroid. So what they do is they can use iodine, I think specifically iodine 131, inject the radioactive iodine in, and you can see the activity of the thyroid. So this is great. This is great. Cold nodule, bad. That normally means there is a tumor there. Hot nodule, not necessarily. It could be just hyperactive, but a cold nodule is definitely indicative of metastasis, or not metastasis, but a mass that's probably cancerous. What is the sum of the coefficients? So we've got some more balancing. So remember, whenever we're balancing, we do carbons or any other elements but oxygen, hydrogen. Normally you do oxygen last or hydrogen. In this case, we don't have any of those. So over here, I would just start with lead. Okay, so lead, there's one over here on the left side, one on the right side, so there's not much to do there. Nitrate, so we have 2 nitrates on this side, 1 on the right side, so let's put a 2 there. Okay, so 2, so that makes 2 sodiums, so let's come over here, 2 sodiums, and then that's 2 chlorines. So let's just write it out real quick. So we've got lead, nitrates, sodium, and then chlorines. We'll have this on both sides. Don't split up the polyatomics specifically. Keep them together if you can. In some cases, they get split, which makes the balancing a little bit harder. But normally keep the polyatomics together. So 2 nitrates, 1 lead, 2 nitrates, 2 sodiums, 1 chlorine, 1, 2, 2, 2. Okay, so I didn't distribute that there. So we have 1, 2, 2, 2. Okay, so now we have all the appropriate coefficients. Remember, it wants a sum. So 1 plus 2 plus 1 plus 2. So that is 3 on this side, and then, 3 on that side. So 6. Empirical formula. These tend to scare students for some reason. I'm not entirely sure. There's just a process to work through. So we're looking at a compound that's 40% carbon, 6.7% hydrogen. Let's put the C over here. Hydrogen, and then 53.3% oxygen. Okay, so the first step, we're going to knock off the percent and just put grams. So that's the first step. Second step, convert to moles. Okay, so 40 grams over 1, and there's 12.01 grams in every 1 mole of carbon. Right, hydrogen, so that's going to be 1.01 grams in every 1 mole. And then here, oxygen is 16 grams in 1 mole. So units will cancel, right? So we're going to see how many moles we have of each one of these. So 3.33 conveniently for the first one, 6.63, and then 3.33. So now the first step, drop the percent grams. 2, calculate how many moles you have, right? So that's here. Next step, number 3, divide by the smallest number of moles. So we have a tie, so we're going to use 3.33. Okay, so that's going to be 1, 2, 1. So now these are the coefficients for, or I should say, I guess the subscripts for our elements. So C1, H2O1. So that is the empirical formula. Whenever we look at the bottom of the periodic table or the atomic mass, that is a representation, the number, like for carbon, right, is 12.01. That is a representation of the abundance of the different carbon isotopes. So if you go randomly, just pick a handful of carbon, there's going to be carbon 12, there's going to be carbon 13, there's going to be different isotopes, but their abundance is essentially how we get this average atomic mass, right? So here we're just working on average atomic mass, which is essentially just the mass times the percent abundance plus whatever the next mass is, plus or times the percent abundance. So just real simply, we have the mass of 12. What is the percent abundance on that? And we're just going to convert it to a decimal. 989 plus 13 times 0.011, right? So just move that over 1, 2. Okay, then we'll be left with 868 plus 0.1313. Add those up. 11.9993 grams per mole. So essentially, if this were the abundance of carbon 12 and carbon 13, this is the average atomic mass that we would use, similar to like the number on the bottom of the periodic table. So this is how you calculate average atomic mass. Just use this formula, and it's pretty straightforward. Sometimes they won't give you the percent abundance. They'll ask about percent, and just remember that if you don't know the percent, you can just put an X here and then 1 minus X for the percent over here. So I see that all the time. So like let's say if they give you, well, this one is 20% abundance and they don't tell you the other one, well, then it's 1 minus 20%, right? So this one would be 80%, right? So just use that expression of X and then 1 minus X if they don't give you the percent. How many atoms of chlorine are present in a sample containing 2 moles of chlorine gas? Okay, and so chlorine gas, and so if you look down here, was actually kind of the first chemical warfare weapon. So they would let the gas out on the fields, and chlorine gas is heavier than air, so it would go down into the trenches and essentially suffocate people. So it's actually a nasty way to go. So you can see here, even at concerts, like whenever they use like fog machines, right? So it's down near the ground, so the gas is heavier, so it sinks to the bottom. So it's kind of interesting. So how many atoms of chlorine are present in a sample containing 2 moles of chlorine gas? So 2 moles of chlorine gas. So that is the tricky part right there, chlorine gas. Chlorine in its elemental form is what? Diatomic, right? So if we have 2 moles of Cl2, not 2 moles of just Cl. So it essentially doubles the amount that we were expecting. So if we have 2 moles, and then 1 mole is 6.02 times 10 to the 23rd. So that's going to give us atoms, or molecules in this case, right? Because we have molecules of chlorine. But then we would have to double that number because chlorine gas is a diatomic in its elemental form. So that's going to give us a final answer of 2.408 times 10 to the 24th. So D is going to be our answer. So the tricky part to this one, relatively straightforward. Just how many atoms are there? Well, chlorine gas, diatomic. Once again, know your diatomics. Which of the following is most likely ionic? Right? So ionic, or an ionic bond, is between a cation and an anion. Right? So a cation, so it's a bond between ions, right? Okay. So a cation, that's the positive one. Remember it this way. I've known it since 8th grade. That's the cation. Anion is negative. So which of the following is most likely ionic? So we're looking for a metal and a non-metal is normally where ionic bonds come from, right? So looking here, glucose. Do any of these look like a metal? Those are all non-metals. So that's some sort of molecule, not ionic. Won't dissolve. In water, it'll dissolve, but it won't like dissociate into ions. Oxygen. So oxygen, remember, that's a diatomic. That's O2, right? But it's a non-metal. It's not ionic. Iodine, another diatomic, I2. It's not metal. Then we have a polyatomic hydroxide, right? Lithium hydroxide. So lithium, that's a positive species. Hydroxide, or anion, lithium hydroxide is most likely the ionic one, or it is the ionic. Which of the following is most likely covalent? So covalent, now we're dealing with a non-metal plus a non-metal, right? So up here we were dealing with a metal plus a non-metal. For ionic, covalent, non-metal, and non-metal. Nitric acid. Okay, so nitric, remember, nitric acid. Argon, it's just an element. Carbon tetrachloride, so carbon tetrachloride, like so. Sodium chloride, NaCl. That's a metal. Non-metal, definitely not that one. That's not covalent. Argon's just an element, so there's nothing, nothing interacting there. Covalent, so non-metal and non-metal. Carbon, non-metal. Chloride, non-metal. Good candidate. Nitric oxide, here we have a non-metal. Non-metal as well. So this one can dissociate though, right? So we can get this in water. So technically this one is ionically bound because it's between ions. Over here, that's our covalent species, carbon tetrachloride. So Jeff Bezos, at the time that I made this PowerPoint, he is certainly much richer than that now, had a net worth of $184.4 billion. How many moles of dollars is he worth? So this is just straight up a conversion problem, right? So unit conversion, 184.4 billion, right? So that would be million. Nice number to see in your bank account, right? So 402 sets of zeros. Okay, so let's convert that into moles, right? So if they're 6.02 times 10 to the 23rd dollars or whatever, so 1 mole is just this many in 1 mole, right? It's like saying 1 dozen. So that's going to come out to 3.06 times 10 to the negative 13th moles. A very, very small number. So this is a very, very large number, but mole is just so insanely large. 1 mole is just crazy. If you have 1 mole of dollars, you'd be insanely rich. So this is just showing you unit conversion and how many moles of dollars Jeff Bezos has. Okay, so our last problem. And this one's going to be a bit of a challenge problem here. Okay, so if you stacked atoms of cesium on top of each other, how many would it take to equal the width of a piece of paper? This is the width of a piece of paper, and we have the atomic radius of cesium. Okay, so essentially, if we stack up the atoms, how many needed to be the width of a paper? Okay, a lot of unit conversions here, right? So we said unit conversions, that's what's going to make you good at chemistry. So this is a tough problem, so see if you can work through this. Let's start with 0.0039 inches. Well, anything in science we're normally dealing not in US customary, right? So let's convert 1 inch, get that to centimeters. Okay, so that's going to give us 0.009906 centimeters for the width of the paper. So we already know how big this is. Okay, so now we have the radius of one cesium atom. Okay, so that's 343. P is pico. So that's 1,000 less than nano. So it's pico is 1/1000th of a nanometer. So we have picometers. Okay, so we got to do a lot of conversion here to get us to centimeters, right? So picometers, there are 1,000 picometers and a nanometer. Nanometer. 1 nanometer. 1,000 nanometers and 1 micro, right? Okay, so then we have 1,000 micrometers in 1 millimeter, right? Next, centimeters to millimeters is not 1,000, right? Okay, so there's 10 millimeters in 1 centimeter. Okay, and there's kind of something tricky here, right? Radius. If we're stacking these up, that's the radius. We got to double that, right? We need the diameter. We need it all the way across. So we need to double 343. So you can just double it back here or just add a 2 on down here. So that's going to come out to 6.86 times 10 to the negative 8th centimeters. And that is the thickness of one cesium atom. So now what we can do is we can take the total width of the piece of paper, right? And we can divide that by the width of one cesium atom. And that will give us the total number of cesium atoms, right? And so that number comes out to 144,402 cesium atoms. Okay, so this was just a big unit conversion problem, right? So we're dealing with going from US customary to metric, a little bit of a trick with the radius, something to pay attention to get the diameter, so we had to double the number, working with our unit conversions from picometers all the way to centimeters, so not necessarily easy, or if you'd even seen picometers before. So this is a good problem to work through, conceptualize, and then practice unit conversions.